Somewhere over the Arctic right now, a river of wind that circles the entire planet just buckled, and what slipped through that crack is something forecasters genuinely did not want to see this early in the season. This is not just another cold snap or another weather headline. This is a signal that the entire pattern controlling weather across multiple continents just shifted, and the consequences are already showing up on radar screens. Stick around, because this gets stranger the deeper you go. Let's start with what the jet stream actually is, because most people picture it wrong. High above the surface of the Earth, there's a powerful current of wind racing from west to east, wrapping around the entire Northern Hemisphere. This current acts like a wall, separating the freezing Arctic air locked up near the pole from the milder air sitting of sea on the rest of us. As long as that wall stays straight and strong, weather stays relatively normal and predictable. But that wall does not always stay straight. It bends, it dips, it curves into massive loops called Rossby waves, and when those loops get big enough, they stop moving smoothly from west to east. Instead, they stall out, they buckle, and sometimes they collapse entirely. When that happens, the cold air that was supposed to stay locked up near the North Pole finds an opening and comes pouring south. This exact kind of event is happening right now, and it is tied to something called a sudden stratospheric warming. This is one of the most dramatic events in all of meteorology, and the name barely does it justice. Temperatures high up in the stratosphere, tens of kilometers above the ground, can spike by as much as 50 degrees Celsius within just a matter of days. To put that in perspective, that is a temperature swing most of us will never experience on the surface in our entire lives, happening in a layer of atmosphere most people never even think about. This sudden spike disrupts the polar night jet, which is the high-altitude engine driving the whole system, and it can cause the entire polar vortex to stretch, wobble, or even split completely in two. Forecasters have been watching exactly this kind of disruption develop, with models showing the stratospheric circulation weakening and elongating well before it typically would in a normal winter. When this reversal happens at the right altitude and the right latitude, its effects do not stay trapped up in the stratosphere. Over a period of 10 to 20 days, that disruption propagates downward into the layer of atmosphere where our actual weather happens. This is the part that should genuinely concern anyone paying attention. Once that downward coupling occurs, it can reshape pressure patterns at the surface itself, triggering what meteorologists call a negative Arctic oscillation. Under this pattern, the jet stream does not just wobble a little, it becomes highly amplified and irregular, opening the door for Arctic air to plunge deep into regions that are used to far milder conditions. We have already seen exactly what this looks like in recent events. High-latitude blocking has strengthened dramatically over places like Greenland and the wider Arctic Ocean, while the normal west-to-east flow of the jet stream weakens and meanders much farther south than it should. This is the buckle. This is the literal crack forming in the wall that is supposed to hold the cold air back. And once that crack opens, what comes through is not subtle. Meteorologists tracking recent disruptions have pointed to a full breakdown of the stratospheric circulation, one significant enough to reorganize weather patterns across the entire Northern Hemisphere for weeks at a time. This is not one cold day passing through. This is an extended pattern shift that can linger deep into spring. If this is blowing your mind a little, that is exactly the reaction meteorologists have when they see this setup developing. So go ahead and subscribe, because we still have to get into which regions are most at risk and why some scientists are actually divided on how much worse this is getting. The regions caught in the crosshairs of these events tend to follow a familiar pattern. Eastern and northeastern parts of the United States frequently face the highest risk of deep freezes and heavy snow once one of these disruptions fully propagates down to the surface. Northern and Central Europe face their own version of this threat, since a weakened vortex allows cold air from Siberia to shift westward into the continent. Even parts of East Asia, including Japan and China, have seen unseasonable cold linked directly to these jet stream shifts. Here is what makes this even more complicated. No single country is truly immune once one of these disruptions gets going, but the regions least accustomed to prolonged Arctic air tend to suffer the most damage. Infrastructure, agriculture, and energy grids built around milder average winters simply are not designed to handle weeks of extreme cold showing up out of nowhere. Some of these disruptions have started earlier than forecasters expected, with satellite and model data showing the stratospheric circulation already weakening and wobbling during a stretch of the year when meteorologists would normally expect calm, stable conditions. That timing alone has raised eyebrows among people who track this pattern every single year, because an early disruption often signals a more volatile winter overall, rather than a one-time event. Layered on top of all this is the influence of ocean temperature patterns, like La Nina, which can redirect global jet streams and reshape storm tracks even without any stratospheric disruption involved at all. When a weak La Nina pattern combines with an already unstable polar vortex, Forecasters have described the resulting setup as one that can transform what should have been a fairly mild winter into a season defined by extreme temperature swings and severe snow events. Now here is where the story gets genuinely fascinating, because not every scientist agrees on what is driving all of this. For years, one leading theory suggested that rapid Arctic warming was directly making the jet stream wavier and more prone to these disruptive buckles. The logic made intuitive sense. As the Arctic warms faster than the rest of the planet, the temperature difference between the pole and the mid-latitudes shrinks, and that shrinking difference weakens the winds that normally keep the jet stream running in a tight, stable line. But newer research has actually pushed back against parts of this theory in a big way. Some researchers, studying 4 decades of real-world observations, found no long-term increase in jet stream waviness despite the Arctic warming dramatically over that same period. Their analysis suggested that while a wavier jet stream and Arctic warming do appear linked in year-to-year and decade-to-decade variability, that link has not translated into a sustained upward trend in waviness over the long haul. Other researchers have gone even further back in time and found something that complicates the picture even more. Looking at records stretching across the entire 20th century, they discovered that the jet stream was actually just as wavy during earlier decades, long before Arctic amplification became a major factor at all. This means the waviness we are seeing today may fall well within a range of natural variability that existed even before rapid Arctic warming became part of the conversation. So where does that leave us? Scientists are essentially engaged in a genuine tug of war over the mechanics here. Climate change appears to weaken the temperature gradient between the pole and the mid-latitudes in a way that should make the jet stream wavier and more prone to buckling. At the same time, other effects tied to climate change are cooling parts of the lower stratosphere and warming the upper troposphere over the tropics, which actually works in the opposite direction and can strengthen the jet stream instead. These two competing forces are pulling against each other, and the honest answer from the scientific community right now is that nobody has this fully sorted out yet. What researchers do agree on is that when a buckle happens, whether from natural variability or an amplified climate signal, the downstream effects on the ground are very real and very disruptive, regardless of which theory ultimately wins out. This uncertainty is exactly why forecasters watch the stratosphere so closely every single winter, monitoring for those telltale signs of a sudden stratospheric warming event forming. They know that once temperatures spike in that thin layer of atmosphere far above our heads, the clock starts ticking on a 10 to 20 day countdown before the surface weather across an entire hemisphere can shift dramatically. For anyone living through one of these events, the practical impact is what matters most. A buckled jet stream means longer, stretches of extreme cold rather than just a single frigid day. It means storm tracks shifting away from their usual paths, bringing snow and ice to places that rarely see it in such volume. It means energy grids straining under sudden demand spikes as heating systems run non-stop for days or even weeks at a time. Travel disruptions tend to follow immediately behind these events as well, with icy roads, canceled flights, and delayed trains becoming the norm rather than the exception for as long as the pattern holds. Agricultural regions face their own set of risks too, since sudden hard freezes arriving outside their typical window can damage crops that were never prepared for that kind of cold at that particular time of year. There's also a domino effect that plays out across the power grid during these events, and it rarely gets the attention it deserves. When a buckled jet stream drags Arctic air across a region for days on end, heating demand across homes and businesses spikes all at once. Grid operators who normally plan for gradual seasonal shifts suddenly face a sustained surge that can push infrastructure right to its limit, sometimes triggering rolling outages at the exact moment people need heat the most. Water systems can take an unexpected hit as well. Pipes that were never insulated for this kind of prolonged deep freeze can crack or burst once temperatures stay locked below freezing for an extended stretch. This has repeatedly caught entire cities off guard in regions where a hard freeze lasting more than a day or two is historically rare, leaving thousands of households without reliable water in the middle of the coldest stretch of the year. Forecasters also point out that these events rarely arrive as a single isolated dip in temperature. Once a stratospheric disruption fully couples down to the surface, it tends to produce a series of cold outbreaks rather than just one, with each new pulse arriving every week or two as the disrupted pattern works its way through the atmosphere. This is part of why meteorologists warn people not to relax after the first cold snap passes, since a second or even third wave can follow close behind. What makes forecasting this even trickier is the sheer complexity of the atmosphere during these transitions. The relationship between Arctic warming and jet stream behavior is not a simple one-direction cause and effect. Researchers have described it as a competition between multiple forces operating at different altitudes and different latitudes simultaneously, all interacting in ways that current models still struggle to fully capture. This is exactly why long-range winter outlooks carry so much uncertainty every single year, even from the most sophisticated forecasting agencies in the world. A subtle shift in ocean temperature patterns, combined with a stratospheric disruption that forms just slightly earlier or later than expected, can completely change which regions end up buried under snow and which ones stay relatively mild for the entire season. What makes this whole phenomenon worth paying close attention to going forward is the frequency angle. Even researchers who remain skeptical about a long-term increase in jet stream waviness acknowledge that these disruptive events keep showing up with real consequences every time they occur. Whether the underlying cause is shifting due to a changing climate or simply cycling through natural variability, the outcome on the ground looks remarkably similar either way, and it is not something anyone can afford to ignore. If you live somewhere that has felt one of these sudden cold snaps, blindside an otherwise mild winter, now you know exactly what was happening thousands of feet above your head days before it ever reached the ground. The stratosphere warmed, the vortex wobbled or split, and roughly 2 weeks later, that disruption finally made its way down to the world you actually live in. So the next time you hear forecasters mention a buckling jet stream or a stratospheric warming event developing over the Arctic, do not brush it off as just another weather story. Understand that a crack just opened in the wall that normally keeps the coldest air on the planet locked away from the rest of us, and what comes through that crack tends to reshape weather across entire continents for weeks at a time. If this video helped connect the dots on something you have heard about but never fully understood, make sure to like it and subscribe so you catch the next disruption before it hits your own forecast.